Thank you. Good morning. I'm very glad to have this opportunity to share with you our center's current effort on developing this new generation or next generation NRBs treating onsite wastewater. So I'll be presenting on behalf of our whole research team. Okay, so as Dr. Y just presented, so the passive NRB system is a promising technology that has shown prominent natural removal from onsite wastewater. As he also mentioned, there are some design concerns and operation issues that led us to think about can we make some modifications or design some new systems that can solve these listed issues. So the center started with a systematic approach. We tried to first use bench scale column tests to prove a concept of our new designs. And then we will scale the system up and let the system treat the real septic tank effluent in our research trailer. And after we collect sufficient data, and then we move the system to a real field installation for long-term monitoring. So how exactly we look at this problem or question? So basically you can see here, this is our overarching goal is to develop this new generation NRBs. So we look at this from three different perspectives. So we ask ourselves, can we optimize the configuration and the operation pattern to improve this system removal efficiency? So can we look into some alternative like filtration materials that we can improve not only the removal but also the recovery of nutrients? So we also look into some alternative mechanisms such as physical chemical removal mechanisms. Can we help the system to perform even better? So the bullet points listed here are current center's efforts. So I highlight these different color bullet points to explain. For example, when we use modular-based system, where we change our loading or hydraulic pattern and use some amendment of natural-based filtration materials and apply some physical removal mechanisms, we can significantly improve both nitrogen and phosphorus removal and recovery. So if we use the optimized system size design like that optimization and use the sensor monitoring, we can increase the flexibility of the system and we can make it more versatile to different locations, not only our locally but also nationally. So by using the by looking into these orchids like longevity and using some biomarkers to track these biological processes, and we can answer some of the operation questions regarding the longevity and the maintenance frequency. So collectively, we will be able to develop these next generation RDs to make them more cost effective and sustainable. So in my presentation, so I'm going to give you a summary of how we approach this from an engineering point of view. So I will start to provide you a summary of our findings in the NRB 1.0, which is the conventional NRBs Dr. Wai just explained. And then I will move to the NRB 2.0, which is our new design that has passed the pilot scale testing, which is currently under field testing. I will also talk about the NRB 3.0, so that is kind of, we just passed the proof of concept stage. Now we just scale it up in the pilot scale test trailer to treat real septic tank effluent. So our next stage is to, based on what we learned from these three different NRB versions, we're going to develop this NRB 4.0, which can simultaneously remove and recover nitrogen and phosphorus. So before we start designing the new system, so we first conducted bench scale column tests. We want to get a mechanistic understanding of how these different treatment layers really works. So here you can see we can construct the different depths of the sand columns in the lab, and we actually identified which environmental factor is the most critical one that governs the nitrification performance. So among different parameters such as dissolved oxygen, alkalinity, and loadings, we found alkalinity is the most critical factor that will affect the overall system performance. We also found when alkalinity was provided sufficiently, so actually the system can achieve a full nitrification at a very shallow depth. So that is very important to tell us that we are able to kind of increase our loading in our new design. We also found the nitrification efficiency is more sensitive to the hydraulic loading change rather than the nitrogen loading change. So in addition to this configuration of operation study, we also tested alternative filtration materials. So here we use the biochar. So some of you may be familiar with biochar. This is a black carbon produced as a byproduct from this biomass pyrolysis. So on the island, we have a lot of farmlands. Actually, we have a lot of biochar sources for us to test from. So biochar has been used a lot in agricultural applications that can provide some nutrients use, increase the nutrients use efficiency, and also provide long-term benefit. However, there are very few studies that people have been using biochar in the wastewater treatment process. So here, we propose if we can add biochar into our current NRB system, they can provide some potential benefits by using via different mechanisms as I listed here. So basically, we constructed bench spill columns by amending biochar at different volumetric ratio from 10% to 100%. And that this columns to treat real septic and effluent in our research trailer. So we conduct experiments for both short-term experiments and also long-term for almost 8 months. And basically, we found biochar amendment actually improved the overall nitrogen removal efficiency for both experiments. So with these materials like study, so actually collectively, these studies actually give us laid a very nice foundation for us to design our next technology. So here I'm going to switch gear to talk about an NRB 2.0 system, which is also called Flex Street Biofilter. So this system was designed and also prototyped by our Associate Director, Mr. Frank Russo. And I'm going to briefly explain how the system works. So NRB 2.0 is a modular-based, gravity-driven, continuous flow biofilter. So here I use different color boxes to kind of emphasize each treatment unit. So this blue box represent 2 replicate nitrification filters through the waste C33%. And after the nitrification step, the flow distributor will separate the nitrified effluent to different routes. So the majority of the nitrified effluent will filter through these replicate intermediate denitrification barrels filled up with 100% of wood chips. And the other part of this nitrified effluent will be filtered through our final quality unit, and the final effluent will get discharged. So in this yellow box, after this denitrification step, our intermediate denitrification effluent will be circulated back to this green box, which is a pre-aeration tank. So here we would combine and mix the septic and effluent with our returning effluent, and this mixture will serve as the influent to the nitrification columns on the top. So the unique feature of this design includes a continuous flow, which is different to most of these passive biofiltration systems. And we provide an internal recycle. We can adjust the recycle ratio. And also we provide an optional pre-aeration system. You can decide whether to turn on the aeration or not, depending on your influent water composition. So here is a photo showing you we installed NRB 2.0 in our wastewater research and innovation facility, where we can treat the real septic tank effluent. So during this almost 3 years pilot scale test, we have been testing 3 different major parameters. We have tested the hydraulic loading rate change, nitrogen loading rate change, and also the recycle ratio change, how they would impact the overall system performance. So here I want to provide you a kind of a snapshot of how the system works. So this is very basic figure. So the y-axis is the total nitrogen concentration, and the axis you can see this is how long we have been operating the system. We're still operating the system. I just didn't put the most recent data in this graph. So you can see we operate this NRB 2.0 at several different stages. And you can see these like black color is influent nitrogen concentrations really fluctuating from 30 milligram per liter to almost 100 milligram per liter. And what is important here is to show you how the system really performs. So if you can see, there's like the purple color represents the final effluent total nitrogen concentration. So during our entire experiment, most of the time we can achieve the final effluent nitrogen concentration less than 10 milligram per liter. And occasionally you may see a little bit higher concentration, but because the influent concentration is always fluctuating, but most of the time we can achieve our test goal to be below 19 milligrams. I also want to mention we shut down the system for about 2 months during the pandemic in 2020. But the system resumed its performance very quickly, less than 2 weeks to the concentration below 10 milligrams per liter. And during the entire experiment, we only observed this like one clogging issue. That is because of we challenged the hydraulic loading in the system by 300%. So that is like, I will address this a little bit in the later slides. So you may wonder, okay, so how does this system performance compare to other systems? So here I present you a table that we want to compare the NRB 2.0 with the other filtration-based on-site system as well as our conventional NRB 1.0. So basically, when we compare these two different NRB systems, you can see their flow patterns are different, but actually NRB 2.0 can achieve a similar level of organic matter removal. You can see the BOD removal and fuel removal efficiency are comparable to our conventional NRBs. But I want to point out here, our influent nitrogen concentration and our hydraulic loading rate has increased by 2 to 3 times. So from the engineering point of view, that translates to a smaller footprint of the system. You can achieve the same efficiency, but actually you can increase loading. So if we compare NRB 2.0 with some other on-site systems, such as recirculating sand filter, constructed wetland, and some other proprietary systems, we found so basically the hydraulic loading and the nitrogen loading are comparable between NRB 2.0 to these systems. However, our TN removal efficiency is significantly higher for this system. So that makes this system really a promising technology here. And after about 3 years pilot test, so now we are entering the stage of field test trials. So this flagship biofilter has been installed in the ground. We are conducting long-term monitoring. We also have a poster in the hallways. If you want to know more details, feel free to check that out. So in the meanwhile, I also want to mention, since I mentioned this like a clogging issue briefly in the performance, I also want to mention some of our current ongoing effort. So we're also exploring some optimal filtration media, either we can replace or amend to our current design. So basically, we want to overcome this hydraulic loading challenge. We can further improve these hydraulic loading, while in the meantime, we can still achieve this desired treatment performance. So here are some of the materials we are currently testing, including the biochars I just mentioned, and also including some industrial waste like marble chips, and also like zeolites. We selected them based on some of their potential removal mechanism. Like marble chip can provide supplemental alkalinity, and zeolite has the potential to remove ammonia as well as phosphorus simultaneously. So here's our lab setup. So the experiment is currently ongoing. So last but not least, I also want to mention our NRB 3.0. So this is another novel design. So how can we come up with this NRB 3.0 design? You can see here, we actually integrated 2 different IP systems. So we started from this proprietary on-site system, which is activated substrate, suspended growth system. So we're thinking that can we integrate this system with our passive NRB design? So basically, we'll be relying on both suspended growth condition and also attached growth condition. And we are substituting our filter media instead of using sand and wood chips. Now we are using synthetic media. So in this way, we are aiming to use less wood chip, and also we want to produce this off-the-shelf product that is more kind of flexible to install in the homeowners' backyard. Also want to optimize our aeration pattern to save energy. So this is our operation strategy. So we call this NRB 3.0. Also, we call this nitrogen removing biofilm reactor. So it is really hard to tell if it's really a activated slab system or it is really a single filter. So you have to look into exactly how their performance is. So we first tried the 2 different configurations, whether we can have a synthetic media only bioreactor, or we can amend some wood chips to facilitate or to provide this external carbon. And we found out when we have bullshit amendment, the system kept at anaerobic condition all the time, so there's no natural removal. So then we focus on this biocarriers only condition. The next question we ask ourselves is whether these different synthetic media type affect overall system performance. So we try different biocarriers type, and we found actually they have little impact on the overall heat removal. And also the system has reached its treatment capacity. So then in order to further improve the system performance, we think, okay, so can we add a polishing unit, maybe use a little bit like a wood chip amendment in the segment, and actually we find a significant improvement of the system. So currently we are operating the NRB 3.0 in our research trailer, treating real septic tank effluent. So here I want to show you, this is the overall configuration. So in this bioreactor, we use two different types of biocarriers to pack it up, and we also install a dissolved oxygen sensor at different depths. We provide this aeration unit at the bottom. So so actually, this system has been operated for several different stages. I just want to provide you a kind of a snapshot. After the system reached steady state condition and with this aeration pattern, so we found the majority of the biomass present in the reactant is actually in these biofilms. You can see this bar is much higher. So no matter what types of biocarriers we use, the majority of the microorganisms who are really removing nitrogen, they are living on the surface of these biocarriers. Only a small portion of the microorganisms are present in the liquid. So that suggests we have a stable and functional biofilm form. So in terms of the TM removal, you can see at stage 5, actually we can achieve a final effluent concentration around 20 milligrams per liter, which is a little bit higher than our ultimate goal, 19 milligrams per liter. But I want to emphasize the NRB 3.0 system, we have no external carbon source limited. We're only relying on the organic matter present in the septic effluent, and that level is really fluctuating. So basically, we want to, in order to achieve a better performance, we add on a 10% wood chip amendment to part of our synthetic media, and we did see a significant decrease of final effluent TN to about 5 milligrams. So these additional polishing unit really work. So here is a photo we took from our pilot scale test in the research trail. At the end of my presentation, I just want to mention, I also highlighted a few bullet points here that I don't have time to really cover those. These are also the current efforts the center is working on. But I'll be very happy to discuss more and also answer the questions from the audience. Thank you.